Um, yeah. So, hello everyone. So today's reading session is about YOLOv9, learning what you want to learn using the programmable gradient information. So my name is Harisatvik Birla. So I'll be presenting this topic today. Okay, yeah. So we'll go step by step from the problem statement, demo, implementation, and then the performance. So the problem statement. So like before starting, this is how the YOLOv9 performs the detections when an input image is given. So you can see how the bounding boxes were plotted for major categories like bowls and bottles and etc. So yeah, what's the problem that YOLOv9 is trying to solve? So like in the existing methods, we see like when the information is passed from layer to layer, so things like spatial transformation and etc., the information will be lost. So that's being defined from the information bottleneck principle. So using the concepts of programmable gradient information and the concept of generalized efficient layer aggregation network, so that's called as GELAN. The architecture is being like fine-tuned on the existing models, and that's how significant performance is being achieved in this. So yeah, next slide. Right, the information bottleneck principle. So this reveals like a fundamental challenge in the deep learning, that the information getting lost in the successive layers. So if you see the formula, the mutual information that is being represented by I here, the information here at the first stage is greater than the second stage, which is greater than the successive layers. So this is how it is being defined mathematically. So this is one of the problem which the authors of the paper are trying to solve. And yes, so the programmable gradient information. So this particular style of design has three components. One is like the regular main branch, the second is the auxiliary reverse branch, and the third is the multi-level auxiliary branch. So the auxiliary reversible branch. So this improves the gradient flow, especially when the information is being retraced back in the back propagations. So unlike the traditional ways, this improves the gradient values and the more details are being captured here. And coming to multi-level auxiliary thing. So here, this aggregates the information from the different layers, and like this supports for the more accurate detection. So since one particular node has the information for all the objects, so the information getting lost is like less here. So the gray part from the picture here, so this represents the auxiliary reversible branch, and the pink highlighted one, so one particular node, if you see, that is highlighted in the gray, that is being receiving the information from the multiple layers. And yeah, so this is programmable gradient information. And coming to reversible functions, so like why reversible functions? So in general, reversible functions allows a network to keep the information flow, and unlike storing all the previous states in the memory and keeping it as computationally heavy, this does not store the values, and by method like backpropagation, it can retract back to the original information that has been received at the starting stage of the information passage. So this is especially crucial for tasks like object detection, etc. And this is one of the significant innovation for information preservance. And like the next one, it's generalized efficient layer aggregation network. So this is based on a previous existing architecture called ELAN architecture, and so this simultaneously takes a different number of parameters, and it's not like computationally heavy. It achieves like significantly faster inference speeds, and that is like varying for different inference devices. So this is being dynamically designed, and we'll see the architecture differences from ELAN and CSPNet. And from the image here, so if you see at the starting A stage, where the input image has a lot of details, so that is not being present in other structures. And whereas if you see in the last structure, the GELAN thing, so most of the details are being captured here, irrespective of the like the depth size of the network design. So the good thing about GELAN style is like this uses the ELAN and along with the information from the CSP structure. So this is like the best of the two structures. And yeah, so this is how the minute features like uh, edges and the coloring information is being captured. And yeah, so the second part for demo. So like this is the output image you have seen earlier. And for the model to do these predictions, code is like pretty straightforward. So you just import its model file, the .pt PyTorch file, and at the last you can directly pass out the image on which you have to do the predictions, and yeah, you will get the outputs in the kind of a list format. And yeah, it's like a short 3-line code. And so the left one is the original image, and the right side is the output which we got from the model predictions with corresponding bounding boxes. And in the output image, if you see at the right side, even the bowls are being detected like only the bowls are like only half size in the image, but still the model is able to capture these kind of details. So which was not there in most of the architectural styles. So different architectures find this difficult in doing predictions on these half size images. So like the live demo, uh, you can directly visit this RoboFlow slash model slash YOLOv9, and you can try out by uploading different images and see for yourself. So now the implementation part. So the YOLOv9 is like a kind of a general and extended version from the YOLOv7 and dynamic YOLOv7 respectively. And coming to the network architecture style, as we have discussed, like since this is based on ELAN structure, this uses an additional blocks like CSPNet, which is also called as cross-stage partial network blocks, and it's like planned with the rep-conv as the computational blocks. So in short, so the GELAN is equals to like the CSPNet's gradient path planning. So that is for capturing the information, and the ELAN's thing of speed optimizations during the inference. So this is how the GELAN architecture is being achieved. And the one more thing that is being additionally implemented is like they simplified the down sampling model compared to the previous architectures. So this is how like the speed has been increased compared to other models. And like the GELAN architecture. So from A and the diagram B, from the A, which receives the gradient values for the better information capture, and from the B, it's for the speeding of inference. And if you closely observe the C thing, you can find that it's a direct an addition of these two different structures of A and B into the C. So this improves the information capturing in GELAN. And so it's actually hard to visualize the YOLO structure in a short slide. So I've added this link. So like netron.app, and you can readily find this .pt file. And if you really want to visualize, like just visit this website and upload the file. So you can see the details of every layer, and you can scroll it out. You can go in detail of how each computation is working. So that's pretty interesting, at least for visualizing. So I would recommend checking this out. And yeah, coming to performance. So it's like pretty straightforward that YOLOv9 has like achieved a better performance compared to other models in terms of the AP percentage and the number of parameters as well. So this was like the off charts. And in this slide, so even in terms of the flops, the YOLOv9 stood out compared to other. And for a conclusion, like what are the pros and cons? So YOLO uh, beats all the YOLO models on COCO dataset with a 41% of less parameters and like 21% of less computational power. So, which is a pretty good milestone at this point, like when YOLOv9 has been rolled out. And like for efficient real-time object detection, this has been improved with like a lot of accuracy and speed support for various devices like even Jetson, Raspberry Pi, and others. But the cons when it comes to YOLOv9 is like uh, this sacrifices some level of accuracy. So you might not be able to get the accuracy like uh, major heavy models, but yeah, some level of accuracy is being lost here. And whenever images has a smaller objects like grouped at one place, like group of images, YOLO finds it hard to detect them. So that is one of the other cons. And yeah, so we reached end of the session. So any question and answers, like if any, so please put it in the chat, or I'll be happy to review them. And you can also visit these links in order to experiment like the custom training of YOLOv9, and you can check it out the paper here at paperswithcode.com. Yeah, thank you.